Everyone, welcome to my YouTube channel. In this video, I'll be talking about doing a MNIST digits prediction using a dense neural network. First, I'll be going through a slide that I have made, and then we'll go through the code. It's the very basic level. So let's start with what exactly is a neural network layout that we are talking about. So in this exercise, we'll be looking at how we are categorizing a digit, a handwritten digit, which a photo has been taken, into a numeric number that we can identify. Now, this task was done quite a long ago, and this was first done by a person called Jan LeCun, which who basically got all these digits, and then he built a model called CNN, that is a convolutional neural network, and then that model was used to make predictions on these digits. But in this exercise, we'll be just using something called a dense neural network. Now, here is a digit. What we do is basically we flatten it. So this digit is 28 by 28 pixels. So if we count the number of pixels in this image, it will be 784. That is 28 here and then 28 this side. What we're doing is basically we are flattening it out to just one. So basically just think of the first line here and then second row of pixels on below that, and then the third row of pixels below that, and so on and so forth. So each of these images is a 784 vector uh, that that we can work with. For some reason it's occurring, maybe I can increase the length. Okay, so for, and what we do is basically this is an input layer, so there are 784 values, and these are float values in the first unit. What we do is we connect this first layer to a hidden layer, and the first layer is basically generally called an input layer. The last layer is always called an output layer, and in between are hidden layers. So we have two hidden layers in this picture. The first hidden layer has 512 units, so if we count the number of neurons in this layer, that will be 512, and the same is the case in the hidden layer too. So if we count this, there will be 512 units. For just demonstration purpose, I have mentioned it 4 and 4 here, and then 3 here. So this is the basic general layout for our neural network. And in between, we also have something called a ReLU. So ReLU is basically what we do is, since we have these connections, this is basically a linear connection and linear formulas. Now to add non-linearity, we add something called an activation layer. So what happens is these activation layers introduce some kind of non-linearity in this process. There are multiple activation functions. There's sigmoid, there's ReLU, there's a tanh function. uh, in this exercise, we'll be using ReLU. I'll be also talking about what exactly a ReLU and sigmoid is. We also have something called dropout. Now, neural networks tend to have, especially the dense neural networks, tend to have a lot of parameters to train on, and this is a good thing that we can generalize a really complex model. But then that also makes it a point that it can easily overfit. Now, to avoid overfitting, what we one of the things that we can do is dropout. I'll be talking about what exactly is dropout in the next slide. So for this slide, I just want you to take away that we have these one-dimensional neural networks. So this is the first input layer, this is a hidden layer 1, this is a hidden layer 2, and this is output layer. And each of these neurons from the hidden input layer and then the hidden layer is connected using a connection, and that will be represented by a weight. We can see that in the next slide. So to talk about the activations, as I mentioned, we have a pretty much linear uh, structure. So this weight will be summation of all these, this, and this weight. So summation of A1, W1 plus summation of A2, W2, and summation of A1, W3, not exactly 3, but they have this will basically call 1 comma 2, because this is the first layer, second layer, so it will be 1 1 2 1 and 3 1 and then so forth. So since we have the summations, it's basically a simple, a linear formula. What we do is whatever we get there, we call it Z, and then Z, uh, we pass that to this activation function to get activation A. So, and activation A will be, in this case, a ReLU of of Z. So, for example, the activation will, in this case, will be max of 0 comma Z. So, if Z is positive, then that's the value. Otherwise, it's basically 0. So here is a graph for the ReLU. As we can see, it's y is equal to x. If x is equal to is more than or equal to 0. Otherwise, it's 0 if it's less than equal to x. And just keep in mind that the function is not differentiable here. So we either take that 0 or 1 depending on what we want to do. Uh, there's a another activation function called prelu that has a slight angle here, and it is differentiable at that point. For sigmoid, the activation looks like this. So the formula is 1 by 1 plus e to the power minus z. And the couple of issues that happen with sigmoid, as we can see, the curve is like this. So if you look at the gradient at this after this, they're pretty much flattened out. And what happens is we get issue of overfitting and vanishing gradient or exploding gradients with case of sigmoid, and even with tanh if we plot that. It just does not happen with ReLU, and Professor Hinton's team, they wrote a paper first suggesting to use ReLU, and then they have been used uh, quite a bit, and in fact almost all the models that people are building. So this is about sigmoid and ReLU. Now let's talk about something about dropout. So as I mentioned, neural networks tend to overfit a lot. To avoid this, what we do is we add dropout. So when I say dropout, this only happens in the training phase. It does not happen in the test phase. So let's think of for a moment that this is our structure for the neural network, right? And all these images I have taken from Google. I will, I have taken from Google, and these might from different blogs, and I've taken them just for making you understand. So think of this as the neural network, and this is the input layer, this is the hidden one layer, this is the hidden two layer, and this is the output layer, as we saw in the last slide. What we do is we assign a value called prob to each of these layers, and if prob is less, and what we do is with each of these neurons, we generate a random number between 0 and 1. And if that number is more than the prob value, then we keep that neuron. Otherwise, we remove that neuron. So for example, let's say the prob in this case is 0.5, and then all these values are randomly assigned in Python or any other language. And let's say this value was 0.7. So since 0.7 is more than 0.5, this will remain here. But this, let's say, was 0.45. Now this is less than 0.5. So this will be dropped off. Now by saying dropped off, what I mean is all those connections that are coming to this neuron, they disappear. What by disappearing, I mean this won't be counted here. So for example, this neuron would have contributed to something to here, that won't come here because this won't come in the forward pass. And the same is the case for uh, this neuron. So this neuron also has the probability value uh, or the a dropout probability less than zero point 0.5. It can be 0.3, even 0.49. It will have the same case, and same with this one. So what will happen is we're forcing neuron not to follow one pathway. So for example, let's say the neuron was learning everything in this particular path, but by reducing this and this to 0, we are forcing the neurons to distribute the weights equally across all the neurons that we see here. and this makes the neuron generalize much better as compared to uh, uh, when we don't have the dropout. And this is in addition to the L1, L2 uh, uh, regularization that we can already do, which in which case we see that the parameters don't get really huge or something like that. Keep in mind that this does not happen uh, in the in the test phase. It only happens in the training phase, where the neurons get uh, dropped off, and this happens at each epoch. We have different neurons that get dropped off. So again, since we don't want the neurons to learn one pathway or assign all the weights to only certain paths and not the others. I'll talk a bit about gradient, forward pass, backprop, and cross entropy. So here is the thing. So think of this as a one neuron. In this case, let's say this, or in this case, let's say this. What we do is there are summations of these input weights, and we forward the z, and z is basically summations of all these previous neurons, and then we have something called gradients that come uh, from the end, that is the output. What these gradients mean is the contribution of this particular neuron in the overall error uh, that we get, and we get the specific contribution of this particular neuron using something called chain rule. And chain rule is basically del s by del x is equal to del s del partial derivative L is with respect to Z multiplied by partial derivative of Z respect to X. And I will suggest to learn more about propagation and these chain rules in multiple videos available on YouTube to understand more about it. But to get an idea, we get a forward pass here, and then in the backward pass, we get the gradients and we update the weights for our neurons using that. So this is the forward pass where we have the 7 and then 7 the digits pass uh, the values here basically multiply with the weights here, and then update these values and update these values and then update these values, and each of these is a softmax. So basically the sum of the probability or the chance of the digits is basically sum to 1. And let's say in this case the 7 is the actual digit, but for some reason the prediction was the highest for 4. So what will happen is, since we are making a wrong prediction, it's a the error will be a lot, and this is calculated something use a cross entropy, which I'll be talking about next. So what we do is basically we let's the error is e, we back propagate this e to each of these neurons, and then each of these neurons, and then each of these neurons using the back propagation. So in the forward pass we go like this. In the back prop we get the final error and then back propagate that error to each of these neurons in our model. The cross entropy is nothing but let's say these are the predictions that we have, and for this case it's S, and this is the actual value, so 100. So let's say we are categorizing 3 classes. Now this is the one hot encoded vector, in which case this is the first class and the rest two are zeros, and these are the predictions, so 0 0.7, 0 0.2 and 0 0.1. So what we do is the error here is basically negative of li log si, so that the li is this one and si is this one. So this in this way we can get the loss or the cross entropy loss for this particular case. So what I've done is I will also visualize that in the notebook, Jupyter notebook. But in this case, these are the digits. So for example, this is 5, 0, 4, 1, 9, 4, 1, 3, 1, 2. As you can see, we can easily visualize these digits here. Um, some of them will be difficult to visualize, I will see, and some of them should be easy. One of the things to look at is the distribution of the data. So we have a training data set, we have a test data set that we can get from the Keras module itself. They provide some out of the box data sets uh, uh, within the module. So as we can see, the digits are from 0 to 9 and in the train set, and the same with the test set. And we can see the distribution across the digits is almost the same for both the training and test data sets. So that should give us some relief that we don't have some kind of a bias or the class imbalance problem that we generally have in a real world problem. In this case, that's not the case. So we can move ahead with the model. Uh, After making the model, we will see that this is the neural network model that we'll be working with. So we have dense layer followed by a dropout layer, and then a dense layer, and then again a dropout layer, and then the final dense layer, basically with output of 10 because we have 10 digits. And this is the accuracy and loss over epochs. So I have trained for 20 epochs of this model. And then on the for this graph, on the y-axis, we have accuracy. And on the x-axis, we have the number of epochs. As we can see, the accuracy quickly jumps from 0 to 97% almost, and then keeps on jumping. And after almost 15 or 15 epochs, the gain is not so much because it has already reached 99, more than 99%. And the curve in the blue is basically the training accuracy, and the curve in orange is the test accuracy. Now we have to keep in mind that the concept of overfitting. So as we can see, the training accuracy keeps on increasing and increasing as we increase the number of epochs, but the test accuracy kind of flattens out just after 3 or 4 or 5 epochs, and there's a quite a bit of gap between them. This might not uh, reflect something called overfitting. The model is overfitting. We will see if that's the case when we look at the code. And this is a loss. So basically, as again in the beginning, the loss starts with around 0.28 or something like that, and then keeps on decreasing as we move forward with the epochs. And this will be inversely proportional. So as the loss decreases, the accuracy will increase. And this curve in orange is basically the loss for our test data set. So as we can see that the loss initially decreases, but then starts to increase back. Again, this also reflects that there might be overfitting problem. Generally, we see that when we're training any machine learning model. Uh, as I mentioned before, that we have these dense uh, uh, layers, and then we have the weight matrices here and here. These weight mat and here as well, and these weight matrices, they have to be initialized to some value because we can't initialize all those values to zero, because it will take there won't be any gradients, and then there won't be any updation of weights. So to do that, we have to initialize with some random number. Uh, Neural networks tend to have something called overfitting and vanishing gradients, and exponential gradients, which means basically if the weights in the neural network are too small, then the signal shrinks, or the shrink or the change in the weights shrink, and it passes through each layer until it's too tiny to be useful. And these are mostly more meaningful for really deep neural networks where we have multiple layers, one, two, three, four, five, even we have hundreds of layers of these hidden layers. And if the weights in the network are too large, then the signal grows as it passes through each layer because there's a multiplication happening and an addition happening at each stage. Uh, Generally, we use something called a Xavier initialization to make sure that the weights are just right. And this was introduced in a paper. It basically draws samples from a truncated normal distribution centered on mean zero and standard deviation of square root of 2 by uh, input number of units, that is the number of neurons, plus the output number of units, that is the output number of units in the tensor. or the neurons. And this is the model we have trained. So basically, this is the weight distribution for the first layer. So we can see there's a 784 here, and then for each of these is 512 here. And then this is the weights for the second layer, and this is bias for the first layer and the bias for the second layer. As we can see, this is almost the same. The centers around zero with a standard deviation of depending on which layer it is. So this was a bit of understanding on what we are going to do in this particular exercise. Let's jump to the code. So here's the MNIST Keras dense neural network uh, in the Jupyter notebook. So the first thing that we do is basically we import the modules. So for example, we import the MNIST. So MNIST is one of the data sets that Keras provides. And then we are working with sequential API right now. I will also share some code when I do something about CNN that will use the functional API. Functional API is much more powerful than the sequential API, but the sequential API is very, very easy to learn. There's not much learning curve and it's pretty straightforward. Then in terms of layer, we're working with dense layers and dropout layers, as I mentioned before. We are using a utility function called toCategorical, which will be looking at what exactly it is used for. When we train a model, we save the weights, and uh, we can again load the model back to a variable in Python for later use. We can also plot the model as we saw in the slides. Then we'll be using some plotting functions, and then we'll be using a bit of NumPy and then display an image. So we're keeping the batch size as 128. So the batch size is basically during each epoch, the with for one epoch, what happens is our model goes to the whole training data set once. Now, if you have listened about stochastic gradient descent or gradient descent, we need to update our weights after either after looking at all the data set or just by looking at every data set. Now, both have their own benefits and disadvantages. The best thing that we do is basically what we call a mini batch gradient descent, where basically we look at certain number of data points before we update the weights, and this works best. Mostly we have them as multiples of two, so it can be 64, 128, 256, 512. Generally, 64, 128 work best with these deep learning models. The number of classes in this case is 10 because we have 10 digits from 0 to 9. The number of epochs that we are training with is 20. As I said, for each epoch, we go over all the data. The model goes over all the data once. Now we will download the data, split the data between training and test set. So Keras provides by default this API that we can use. I already have the data set on my machine. If you are doing this for the first time, it will take a little bit more time as it will download the data on your local machine. Now let's plot these images here. So this is a simple code that I wrote for using matplotlib that plots the images and then has a title with the true label is. So for example, the true label is 5 here and the image is 5, and here is 3, here is 1 and 4. We'll see how our predictions fare against these images in the test set. And here is the distribution of digits in the training set and the test set that we saw before. As we can see, the distribution is fair enough. There's not much uh, discrepancy in the number of image versus the other. Now, since we're dealing with a fully connected network, we need to flatten out these images. Inherently, these images have 28 comma 28 pixel, so we flatten out to 724 length vectors. So this is what we do here. So we reshape the values since we have 60,000 training samples and 10,000 test samples. We reshape to 60,000 and 784. So the 2828 becomes 784. and then here as well, and then we convert them to a float value and then divide by 255. So all these pixel values are between 0 and 255 before this. What we do is basically we normalize that here in order to ensure that the training converges as soon as possible, since we'll be dealing with lesser weights. So we have 60,000 training samples, 10,000 samples, and here's what the categorical two categorical in the Keras utils did. So before converting to categorical, we had the first Y train as 5, and then after converting to categorical, it's 0, 0, 0, 0, 0, 1, 0, 0, 0. So we see the sixth element, or the value 5, is 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 uh, is 1 here, and this is what we'll be using to train the model. And why? Because as you remember, and we saw the case for the cross entropy. So what we need to have this one, and everything else should be a 0, and when we get the probabilities, we convert get this loss. So that's why we need to convert this to a categorical, or a one hot encoded vector. This is the model. So we initialize a sequential model, then we add the dense layer with 512 units, activation as ReLU, input shares at shape as 784, comma 1. So since we are dealing with unit vector, since we are dealing with the flattened out images which have 784 values in it, so the input shape will be 784. And since this is a one-dimensional array, we don't have any value here. So if tomorrow we are dealing with colored images, then we will have the the height, the width, and then the number of channels in the image. In this particular uh, in this particular case, we have just a black and white image, so that's why we have a 784 here and nothing else. We can name these uh, and these layers of some name, so that we can call them later on, which we will see when we do something with tensor board in the future lessons. Then we add a dropout with 0.2. So as I mentioned, if the probability for that particular neuron is more than this, it will stay, otherwise it will be dropped off. Now in general, we keep this value high depending on what exactly this is. When we're dealing with CNN, the closer this dropout is to our actual images, we keep it less, and the further it goes, we start to make it higher. And this is mostly because we want more and more data to flow from here, and then once we start to get later on, then we that information is uh, is distributed across multiple channels, and having some of them dropped off won't make such a huge difference. But if it's very near to the actual image, that might make a difference. But again, this is one of the hyperparameters that has to be tuned in order to get a really good performance of the model. Same with the dense units here. Then we also have this again, one more dense unit with the same value, and we have name as dense2, followed by a dropout with 0.2. And then finally we have our dense with number of classes, that is 10, and activation as softmax. So keep in mind what activation softmax does is, whatever probability values we get here, it 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 basically thrashes that to values between 0 and 1, so that's such that uh, this all these values sum up to 1. All these values that sum up to 1, and this is basically uh, a simple formula here that is working here. So now let's look at the summary of the model, and the summary is this. So basically this is what we built. So the first dense layer has 400 around 400,000 values to be trained. Then we have the dropout, which does not have any parameters. Then we have a dense 2, which has around 262,000 parameters, and then we have a dropout 2, which does not have anything. And then we have the last dropout, which has uh, 5130 parameters. So now we can think of this as weight plus bias. So the weight will be 512 into 10 plus 10. So 5120 plus 10, that is 5130. And the same will be for this. So if we multiply this and add 512, this we will get this value, and so on and so forth. So always keep in mind that we have bias. So we have total parameters that we need to train is around 60-70,000, which is huge, uh, and our model can overfit. So next we need to compile our model, and this is how we compile the model in Keras. Then we need to fit the model. So the fitting of model is done through xtrain, ytrain, which we pass to the fit function. We also pass the batch size, the epochs, the verbosity. So if the verbosity is 1, then it will print out what exactly it is doing. And then the validation split is zero point 0.1, which basically gives an idea how much data I should validate on, and we'll see in a minute what that means. So now we had 60,000 samples in the training set, 10% gone. So that means we are only training now on 54,000 and validating on 6,000 samples. So it's in the first epoch, we have we go through all these 54,000 uh, s- uh, 54,000 training examples here, which is done in 9 seconds. So this is really fast because it's not a really tedious task, and we have a almost shallow neural network. The loss starts at 0.2643 and accuracy starts as 0.9174, which is really good for this small neural network. And then once we start training for 20 epochs, this is where we finish. So in the 28th epoch, the training loss stood at 0.0179. The training accuracy was almost 99.57%. The validation loss was 0.1003, and the validation accuracy was 98.47%. So there is a small difference between this and this, which might again make us think if our model is overfitting, and we can see by looking at the data or the predictions that if that is the case. Here's a plot of the accuracy over epochs. So we can see the same thing that we saw in the slides. The accuracy increases with the training accuracy increases with the epochs, but that is not exactly the same case with the accuracy. It is more of a stagnant after here. We might need to smoothen it out a little bit if possible. And this is the training loss. So the training loss again decreases with the number of epochs, and the test loss first decreases and then starts to increase a bit. So you might say again there's a slight overfitting that might happen here. We now our model is trained. We get the predictions on the X text, and then we plot the digits that were classified correctly. So we said the prediction was 7 here and the actual level was 7. The prediction was 2 and the actual level is 2, and then so on and so forth. So we have 10 random digits that we have chosen here. Now let's look at some of those predictions where we predicted wrong. So the prediction was 5, the label was prediction was 6, the label was 5. This is difficult to understand even for a human, but we can see why the neural network might have failed here. Now here the prediction was 3, but the actual label is 2. So we can see the model not performing really good here. Here the prediction was 2 and the model said 4. Maybe the neural network was thinking that this is the top of the 2. And here the prediction was 0. So I think this played a larger impact in this. So as we can see, the neural network, first of all, has limitations when it is a densely connected neural network, and then that too, there might be a case of overfitting. So we can see this is a really easy case. It should not have been predicted 3, where the actual label is 9. So this is the test loss, the training test and training accuracy here. After we have trained everything, the next case is basically to save the model. So It's very easy in Keras. Whenever we want to save, we just say model.save and provide that path. It saves that in a H5 file, which stores all the necessary weights and the structure of our data of our model. And then once we have saved the model, if we need to load the model, we can use the load model and pass the path where the model was used, and it will basically load the model back into any variable we want. Now let's look at the weights and bias for this for the dense layers that we had. So we had two dense layers. Let's get the first dense layer, and we have again the weights and bias here. So let's look at the config here. So uh, the name is dense one. It's yes trainable. The input was none comma 784. So the none means basically, if you look at TensorFlow code, it means it means the number of training examples that will be passed in a batch. So in this case 128. So that is none. The data type is float. The number of units is 512. The activation is ReLU, and the kernel initializer was variance scaling. So that is, I think, by default. We did not put that value. The bias initializer was 0 at first, and then we'll see that it does not remain 0 when we train the model. Then there was no kernel regularizer. We can also add regularizer so that the weights don't uh, increase the exponential limits. When then we have a bias regularization, not for this case, and these are the configs for that. Now this is the plot for the weights for the first dense layer. As we can see, these are almost normally distributed across uh, 0, and this is the bias for the first dense layer. Then for the second dense layer, here we again plot the values for weights and bias, and then we'll look at some of these values. So for example, for the first layer, we have these are the values. So these are like 5.14 into 10 to the power minus 3, and so on and so forth. So these values are really small, and most of them are less than 1. Not sure if I see any value that is more than 1. Then we plot the model. So basically we can save the model to a PNG file, which we pull out here, and then I had in the slide. So this is the model we trained. It's by no chance a really good model. It's a very basic model, but as we can see, it did a really good job. And just is in I think if we just for trained for 3-4 epochs, we could have gotten accuracy of almost 95%, which is really good for this simple model. So with this, I will stop this tutorial, and I will upload this code on my GitHub, and also link this video tutorial from YouTube on my blog post. If you like my video, please subscribe to my channel and like this video. Thank you.